If the E0 of the cell is positive in value or higher than 0, that means the delta G0 will be a negative value, and of course negative value of delta G means that we have a spontaneous reaction. We can also correlate the delta G that we have learned in the previous chapter, where delta G0 is equal to minus RT ln K, and the K is the constant of equilibrium or equilibrium constant. And now in this chapter, we study that delta G0 is equal to minus NFE0. Therefore, if we combine these two equations, we will get that E0 is equal to RT divided by NF ln K. R is the ideal gas constant, T is temperature in Kelvin, N is the number of electrons involved or transferred in the redox reaction, F is a Faraday constant, and K is the equilibrium constant that correlates with the redox reaction. Now, if and only if you work with the room temperature, so the T is 25 degrees Celsius or 298 Kelvin, we can convert this equation into E0 equal to 0.0592 divided by the N, which is again the number of electrons involved in the redox reaction, log K. And the unit of this will be in volt or V. You can use this formula as well if we work in room temperature, so we can put the T here being equal to 298 Kelvin. So before we have discussed about the standard systems where every concentrations of aqueous systems is 1 molar and every pressure of all gases is 1 atm. So non-standard system of course also exists where the concentration of the aqueous is not equal to 1 molar and the gases does not give 1 atm as the pressure. In this situation, we will use the Nernst equation, which is equal to E0 minus RT per NF ln Q. Now, E is of course the potential of the non-standard state, so potential non-standard. E0 is the standard one, like we have discussed here. So this one is standard. This one is standard from E cathode minus E anode. That's standard as long as you see the 0 superscript. This one is non-standard without the 0 superscript. And this one is standard minus RT per NF ln Q. R is the ideal gas constant. T is temperature in Kelvin. F is the Faraday constant, which is this number, and N is again the number of electrons involved in the redox reaction. And Q is basically a constant for equilibrium. The Q is going to be equal to the product power to its coefficient divided by reactants, also power to their coefficient each. So something like that. Now, sometimes you have heterogeneous reaction where you have aqueous form but also gas form within the very same reaction. In this case, for the gas system, you should use the pressure, so pH2 like this, and of course the unit shall be in atm, which is not going to be equal to 1 if it's non-standard. While for the aqueous system, you will use the molarity. Don't forget again, power to the coefficient, which is to the second, because here you have 2. So down here, you will use molar. And the molarity in non-standard situation will be not equal to 1 molar. Now, especially for reaction that involve H+ like this, sometimes this is also connected to the previous chapter, which is the pH. And simply, all you have to remember is that their mathematical correlation, which is pH, is equal to minus log of the H+, where the H+ is the molarity that you can use in here as well.